Dr. Saurav Chakrabarty, working as an associate professor in the computer science group at the Chennai Mathematical Institute, Tamil Nadu. Before joining Chennai Mathematical Institute, he was a postdoctorate at the Algorithms and Complexity Department of CWI, Amsterdam, Netherlands. He was a postdoctorate at the Computer Science Department of Technion, Israel. He was awarded PhD in Computer Science from University of Chicago. His area of research is theoretical computer science. His focus has been in the classical and quantum complexity of Boolean functions, including property testing, sensitivity, block sensitivity of Boolean functions, and quantum database search in electronic commerce, in graph algorithms, and in coding theory. He has published several research papers in both national and international journals.
Welcome to the UGC lecture series in computer science, and the topic is algorithms. So, today we will be continuing our studies on all pair shortest path problem. So, in the last lecture we had seen one such algorithm. Today we will be looking at another of those. So, to begin, we have been given a graph G which has n vertices V1 to Vn and various edges which are pairs of vertices E1 to Em. Now, here is an example. We draw these vertices on the plane as nodes or circular objects, and we represent the edges by a straight line joining the two vertices that corresponds to it. Example of a graph, and we call it an undirected graph. Each of these edges can also have various numbers assigned to it, and we called it as the weighted undirected graph. And these edges can also have some direction. So, when we say that it is undirected, it means that if u v is in the edge set, then v u is also in the edge set, but that need not be the case. For example, in this example, say d b edge from d to b that goes in this direction. So, d b is an edge, but b d is not an edge. So, if this is the case, we call it as a directed graph, and since it has weights on it, we call it as weighted directed graph. So, usually the distance of unweighted graph is the length of the path from between any two vertex. Now, the length of a path between any two vertex is the sum of the edge weights that have been assigned of all the edges in the path. So, the distance of u to v is the length of the shortest path from u to v. One can think of it as just a map, and which we have some particular cities or say houses, and we have the distance between any two pairs of cities, and we want to find the distance of one city to another city. Now, of course, in such kind of problem, the typical problem is to find the shortest distance of one vertex from another vertex, or in other words, you can say that shortest distance of a city from another city. We can also ask a more general question, what is shortest distance of any vertex from a say vertex v, and we have seen that this can be asked using this BFS. The BFS can work only when it is unweighted, but when there is a weight assigned, that means each edge has been given a real number, then the length is the sum of the weights of the path of the edges in the path, and then we can again similarly define the shortest distance of u to v as the length of the shortest path from u to v. Say here is an example, and consider these two vertices g to a. Now, here is a path, a directed path means all the edges are in the right direction, and the length of the path is say 9 plus 5 plus 8 plus 7 is 29. You can also have another path say like this, which is say 23. You can have another path which is 22. So, in other words, given a graph, a directed weighted graph, there might be multiple paths from one vertex to another, and we want to find out the shortest path from one vertex to another. Note that the weights that are assigned to these edges does not necessarily represent the distance, they can represent something very different things. As we had discussed earlier, graphs are used to model various mathematical problems or algorithmic problems. So, it is not hard to believe that the weights can also represent some negative numbers. For example, in this graph, say weight of the edge E to D is -5. So, it is a negative number. Of course, now when we have negative number, the distances can change. For example, again we have this path from G to A, which is length 29. We can have this path from G to A, a new path of length 23. We can have another path of length 22, but now we can have this path is 9 minus 5 plus 5. So, sum of it comes to 9. So, negative weights are possible, and in that respect we have to define the path weights accordingly. So, if there is a cycle meaning a path that starts from a vertex and ends on the same vertex and has total weight negative, then we call it as a negative cycle. For example, say in this graph, this cycle GEC is a negative cycle. So, a cycle length is -2. Now, when that is the case, it is not hard to imagine that I can take a walk from G along this cycle infinite number of times, and then I will go from G to A. So, I will keep on going around this cycle, and then finally, I will go to A. So, in other words, the shortest distance will become minus infinity. So, therefore, negative cycles are somewhat of an unrealistic setup, and we tend to avoid it. So, in general, we have looked at the single source shortest path problem, and we have seen that if all the edge weights are positive, then we have a Dijkstra's algorithm that runs in order v square steps. If for all other weights, but as long as there is no negative weights, Bellman-Ford algorithm will find out the shortest path of a single source shortest path problem in order v cube steps. A natural generalization of this question is that, say I given a map or a graph, and now I ask what is the shortest distance between any pairs of vertex. I give you u v, for all u v you have to give me the shortest this path from u to v. Now, one obvious thing that can be done is that, since Dijkstra's algorithm and Bellman-Ford algorithm will find the shortest path of any vertex from a particular given vertex u. So, I can run that Dijkstra's algorithm or Bellman-Ford algorithm from various of these u's. I run it from all the possible vertices, and then I will get the shortest path from all pairs of vertices. So, clearly Dijkstra's algorithm therefore, will take order v square times order v. So, order v cube, whereas Bellman-Ford algorithm, which can also handle negative weights, will work for order v to the power 4. The question is that, can we do better? And the simple answer is dynamic programming. It is something that we have seen it in the last lecture. The dynamic programming is a very simple concept, although it is very hard to grasp sometimes. So, you break this problem into small sub problems in such a way that the sub problems are easy to solve, and you store the sub problems answer in a table. Maybe sub problems can be solved recursively, and then using this answer that have been stored in the table, you try to solve the main problem. So, let us quickly go over the dynamic programming that we had seen. Note that we are trying to find out the all pair shortest path problem. So, it defined this new concept called DLUV. This is the length of the shortest path from u to v using 2 to the power L edges. So, dynamic programming defining this object is possibly the hardest part. Once you have defined this object, then half of the battle is done. When you define the right way, you will see it again more in the coming few minutes. Now, what is d0 of uv? d0 of uv is the shortest path of length 1 from u to v. Now, that can only happen if uv is an edge, and in that case the shortest path is of course the weight of the edge uv, and otherwise we note it as minus infinity. Now, here is the beautiful thing. I have defined the DLUV and we can see that if we want to calculate dluv, what is it? So, it is shortest path of length L 2 to the power L. It can be either, anyway the shortest path is of length less than 2 to the power L minus 1. So, that would be this setting dl minus 1 uv, we have no worry about it, or shortest path from u to v of length less than 2 to the power L might be more than 2 to the power L minus 1. In that case, there exists a w on the path such that this w falls in such a way that if you follow that path, this path will give the shortest path of length 2 to the power L minus 1 from u to w and shortest path of length 2 to the power L minus 1 from v w to v. Or in other words, if you sum them up, you get the shortest path and take the minimum over all the possible w's and this object, and you will get dluv. So, the idea is very simple, but just like the case of recursive algorithm, you cannot just call these sub problems, because we might have to store them somewhere. So, here is the graph that we are looking at, and what we do is that we keep a matrix is a b c d e f g and a b c d e f g on the column, and every place I will put the weight of the shortest path from say C to D in this column of length less than 2 to the power L. So, I will solve this particular matrix for all the possible values of L. So, for example, say D 0, all I have to need to put down is the set of places where there exists an edge. Now, for D 1, I might have to look at the shortest path of length 2. For example, consider this graph, this path from G to E. Now, path from G to E right now tells me that it is of length 9. So, what is the best path of length less than 2 to the power 1, which is 2, can be either it can be this path or it is via some other path. If it is via some other path, let us look at all possible other vertices and try to go from G to that vertex in less than one path, and from that vertex to E in less than one path. And therefore, say here we can see that if you can go from G to F, I can go in 11, and I can go from F to E in minus 8, and therefore, if I sum them up I will get 3. So, that means, if you allow me to take a path of length 2, there exists a path of length 3. Similarly, we can keep on doing this for various other settings, and we keep on solving them till at some point of time we stop. Now, question is that where do we stop? I can keep on doing it. I just have defined d l u v. Why did I stop at d 3 in this setting? Note that what does d 3 say? D 3 says that at this point I have the information of the shortest path between any pairs of vertices of length less than 2 to the power 3. 2 to the power 3 is 8, and the total number of vertices that I have itself is just 7. So, the shortest path cannot be more than 7 any case. So, we can stop at this stage. So, in other words, we need to just go on till of d l for L to be something around log v. So, here is the pseudo code. So, for I equals to 1 to log v, we keep on updating our table, and at the end we will get the final table, which is d log v u v, or that table, and that will have all the information that we want. Now, what is the correctness of this algorithm? I had defined it already. It is because that if say v 1 v 2 v k is the shortest path from u to v of length 2 to the power l, then there must be another w such that this v 1 to v t is the shortest path of length 2 to the power l minus 1, and similarly from u to w, this one is the shortest path of length from w to v. Why is it true? It is kind of easy to think, correct? if I am going, if the shortest path from my house to the airport is via your house, then from your house the shortest path must be the same path. If there is some other path to the airport which is shorter than this path, then I would have gone to your house and taken that path. So, any vertex that is in this path P, so for example, any Vi here, the P will be shortest path from say U to Vi and similarly Vi to W. The runtime, it is kind of easy. Every time we have to do a minimum over V objects and we have to maintain this whole V square matrix. So, we get order V cube and I have to run it for L to be 1 to log V. So, I have to go for V cube log V. So, clearly this is much better than Dijkstra's and Bellman-Ford. It can handle negative weights and can do for order V cube log V. Question is that can we do better? We will take a short break now. After the break, we will see how one can use the dynamic programming slightly more cleverly to obtain a better algorithm. So, welcome back after the break. Before the break, we saw how to use the repeated squaring algorithm to obtain a order V cube log V time algorithm for all pair shortest path. The question is that can we do better? The answer is yes, and basically we have to use a clever implementation of dynamic programming. As I told you earlier, defining that object or sub problems like DLUV, that is the crucial of whole of dynamic programming. So, dynamic programming has two parts, sometimes called the head and the heart. The head is the defining that object DLUV and the heart is how to solve DLUV using the sub problems. So, let us look at the Floyd Warshall algorithm. So, here let us start with numbering the set of vertices. So, I number the set of vertices as say V1 to Vn, and now I define DLUV as slightly differently. We define DLUV to be the length of the shortest distance from U to V such that the intermediate vertices are from V1 to VL. I am not saying that here the length has to be less than L, or I am not saying that the length has to be greater less than 2 to the L or such things. Here you are not allowed to use vertices other than V1 to VL. It is something like somebody has told you that okay, you can come from my house to your house, but you can only step on intermediate places where there is no curfew and there is some curfews on some set of vertices. Once you have defined this head, how can we define the shortest path? The shortest path is again easy. So, here again DLUV is the length of the shortest path from U to V that uses intermediate vertices only from V1 to VL. Now, what can this path be? Either this path did not use the VL, in that case the shortest path of length from U to V using V1 to VL will be what is defined by DL. So, DL plus 1 UV, I might not use the last vertex VL plus 1. In that case, it is exactly same as shortest path that I had in the earlier problem. Or the other option is that I had used the last one. In that case, I can use the last vertex. I can use DL to go up to that vertex. Actually, this must be plus 1 and similarly this must also be plus 1. So, either I can go from U to VL plus 1, but intermediate vertices can be only V1 to VL, and I can go from VL plus 1 to V and the intermediate values can be again V1 to VL. Note that why am I focusing on V1 to VL? Because how to go from any vertex to any vertex using V1 to VL is something that is stored in our table. There is a sub problem that has been solved. So, once you solve that, you can use this same kind of stuff to obtain dl plus 1 uv. Crucial thing, what this one is better than squaring, repeated squaring algorithm that we saw just before the break, is that here the minimum just contain 2 values. Remember, there the minimum contain minimum over all possible vertices. So, let us see some example here. Here d0, d0 meaning I am not allowed to use any vertex. If I am not allowed to use any vertex in the intermediate stage, then how can I go from one vertex to the another? The only way I can go from one vertex to another if they are adjacent, or in other words, if I can go from 1 to 4 only if there is an edge from 1 to 4. So, I have 1 to 4, I can go by 9, 1 to 2 I can go by, and so on. Now, in the next stage, what is it? Is d1, mean I am allowed to use the first vertex. First vertex is quite useless, nobody will be able to use the first vertex anyways. So, the first vertex will also be same. Now, comes the second one, d2. In the case of d2, I am allowed to use the first vertex and second vertex. This is where things become interesting. Say from 1 to 3, right now I was having no edge from 1 to 3 and therefore, I could not go, but now I can go. How? I can go to 1 to 2 and from 2 to 3, and 1 to 2 I can go without using any vertex, and from 2 to 3 I can go without using any vertex. So, I will get from 1 to 3 I will get a path of length 15. Similarly, from 1 to 4 I could have gone from 1 to 2 with path of length 8 and 2 to 4 a path of length minus 8, and then I would get 1 to 4 of length 3. So, similarly, I can keep on filling this one and I get this as d2. Now, d3, what is d3? d3 is where I can use 1, 2 and 3 in my intermediate vertices. Now, 1, 2 and 3 in my intermediate vertices, so I can go from 1 to 3, I can go to 7 and so on. I can go to 1 to 3 using 15 steps, and from 3 I can go to say 7 using 5 steps. So, I will be able to go to 1 to 7 in 20 steps. Similarly, say 4, I can go from 4 to 3 in 5 steps and 3 to say 6 in 9 steps. I can go from 4 to 6 in 14 steps. Now, but that is not good. 4 to 6 I can go in 14 steps, that is not good at all, because I already have a path of length 7 to 4 to 6. Anyway, I will take a minimum of those two and therefore, it will remain as 7. So, similarly, we can keep that one and give d3. Now, say d4, again how do I do it? So, let us look at it. From 1 I can go to 4 in 3 steps, and from 4 I can go to 5 in 1 step. So, I can go to 1 to 5 in now 4 steps, because I can use the 4th vertex now, or similarly I can go to 1 to 4 in 3 steps and say 4 to 3 in 5 steps. So, I can go from 1 to 3 in 3 plus 5 8 steps, which is better than what I have right now 15. So, similarly we can do it and we get d4, and again we will do d5 and then d6. Say for example, here say we have d6, and here say for example, we have I can go from 1 to 6 in 10 steps. So, I can go to 3 and then 7. Now, is this the best? No, because if I look at d7, I will be allowed to use any vertex basically, or 1 to 7, which is in our setting the whole vertex set, to go from one vertex to another. And in that case, I can go from 1 to 7 in 13 steps and 7 to 6 in minus 7 steps. So, I can go to 1 to 6 in only 6 steps, whereas 1 to 6 is now 10. So, in that respect, I can go like this and then I can go this. So, this way I can get say d7. Now, once I have d7, am I done? Yes, I am done, because at this moment, by definition, d7 says that what is the shortest path between any two vertex using v1 to v7, and v1 to v7 is all that is there. So, basically it is the shortest path from between any two vertex using any vertex. So, this table is the final output that we are looking for. If I look at this table, you can say, oh, okay, go from 2 to 4 in minus 8 steps and so on. Now, So, this is the pseudocode. Again, as I told you, the dynamic programming pseudocodes are very easy. You define this D0 u v, initialize it, and you just look at this thing. Note that the crucial point of dynamic programming, I repeat once again, is the definition of D u v or D I u v. The definition is something that is not written in the pseudocode, but this is the main part that kind of proves the whole theorem. This is why the theorem works. The correctness of this algorithm, again, if the shortest path from u to v using v 1 to v I, it can be either of two of them. It can either be the shortest path of u to v using v 1 to v I minus 1, or you go take the shortest path from u to v I using v 1 to v I minus 1, and from v I to v using v 1 to v I minus 1. That is obvious, correct? Either you do not use the v I, or if you are using the v I, you will come to v I, and then from v I you will come to the next one, and that is how we get this. The runtime, as I told you, everything is same as the earlier one. Here we have to go up to v steps. So, I have every time I have to maintain a table of size v square. I have to run it for d I, this I has to go up to v cube, but for filling up this table, for each one I am just using minimum of 2 objects. So, it is just a constant. So, I get a runtime of order v cube. In Floyd Warshall algorithm, we can find out the all pair shortest path in order v cube steps. Note, whatever I have done till now, be it be Bellman-Ford, Dijkstra's, repeated squaring, or Floyd Warshall in all pair shortest path or single shortest path, I have always shown you the how to calculate the shortest distance. Note that all these algorithm can be tweaked a little bit to obtain actually what is the shortest path. I will not be doing that one, I will leave it to you as an exercise. To summarize, single shortest path, Dijkstra's was v square and it worked for positive algorithms. Bellman-Ford is v cube, it worked for everything, and for all pair shortest path, basically we have for negative algorithm order v cube or negative weights, we have order v cube algorithms, which is the best. As I told you, the output can be modified to obtain the shortest path. To summarize today's lecture, we had looked at the all pair shortest path in a graph, and we did the Floyd Warshall algorithm for finding the all pair shortest path algorithm. So, with this we come to the end of the shortest path finding algorithm.